So, the goal that we have, let us say, to find approximate nearest neighbor at scale, right. So, what does at scale mean? It means that we want to do this quickly. What does quickly means? So, what I mean by that is sublinear in n. So, in other words, what we are saying is I have n points, but if I want to find the nearest neighbor, I do not want to compute somehow the distance to everybody. That is what sublinear means, right. So, linear means you are looking at every data point at least once. But if you want to get away with that, because there are too many data points, 10 to the 9, massive, then you will have to do this by not looking at some data points. And that is the question that we are asking, right. So, can we get away with not looking at many data points, most data points if possible, and still produce an approximate neighbor, right. So, that is the question we are asking. And if we manage to do that, then we are going to call this a sublinear algorithm. Now, why is this, I mean, where is this sort of intuition, right. So, we want to kind of ask, is this even possible, right. So, we are going to not look at some points, but then that means that those points may be nearest neighbor, but then we are missing them out, right. So, we have to be careful about that, but we know that we cannot use JL, meaning I cannot use JL and then do a linear search in the low dimension, because that is still linear in n, which is what we are trying to avoid. But JL gives us in some sense the intuition to develop the algorithm to solve this problem. What do I mean by that, right. So, we can gain intuition from JL. What is the intuition? So, JL says, well, if I map from high dimension to low dimension, the distances are preserved, right. So, which means that closer points get mapped to closer points in low dimension, right. So, original closer points in high dimension gets mapped to closer points in low dimension, right. So, all the distances are preserved, which means that the closer distances are also preserved, the further distances are also preserved. So, then our idea for this is going to be use JL like intuition, but you cannot use JL directly, but then do something, we will see, we will do something very, very close to JL, but in a slightly different way, right. So, basically what we are going to do is we are going to use this computer science technique called hashing, but then we are going to do it with a twist, right. So, what is hashing? So, you have again these n points in high dimension. So, this is in, let us say, Rn, and what we are going to do is we are going to assign buckets to these n points, right. So, call these finite number of buckets. So, what happens is we want to somehow so let us make these points slightly bigger, so that when I put them in buckets it becomes clear which one goes where. Yeah. So, what I want to do is I want to somehow find a map that puts these points inside buckets. Maybe this goes here, maybe this goes here, I do not know, maybe this goes to this bucket, this maybe, I do not know, goes to this bucket, probably not this one. Maybe this also goes to this bucket, and so on and so forth, right. So, basically think of it as there are a finite set of buckets and you have a bunch of data points. and then I want to put the points into buckets, right. So, now what happens is the points are all here, some points are here, some points are here, maybe some points are here, a lot of points are here, depends on the mapping that we are using. What's the idea now, right? So, the idea is now I get a query point, right. So, I get, let us say, a query point. Now, what I am going to do is I am going to do the mapping for the query point, right. So, I am going to put the query point also, see which bucket it falls in, and that bucket already has a bunch of data points. Now, I am going to only look at the points in that bucket and then measure distances for those points and find the nearest neighbor among points in that bucket, right. So, which means that I am kind of, if the ping point, the query point went to the first bucket, then none of the other buckets matter. So, which means that if I had only a fraction of points, the original points in this bucket, then I am in good shape, because I am not going to look at all the data points. I am going to do something like a sublinear number of, I am only going to look at a partial data set. Now, so which means what do we want, right? So, we want in the ideal case, we want the good guy, that is the nearest neighbor, to be hashed to the same bucket where the query point gets hashed to, yeah. And because we are looking for the nearest neighbor, then somehow the way that we map these points to buckets should map closer data points to similar buckets. That is the intuition, right. So, if 2 points are close in the original space, then they should get into the same bucket, so that if they happen to be, if the nearest neighbor of a different point, that point, a query point, that point will also get to hash to the same bucket, right. So, which means that the chance, well, I am not talked about probability, which means that so eventually you will talk about probability, but then you are somehow more likely to find the nearest neighbor in the bucket where the query point gets hashed to. So, this type of technique is what is called as locality sensitive hashing, right. So, the hashing, the way that we are going to map data points to buckets depends on the locality, right. So, the closer ones get somehow mapped to the same bucket, right. So, that is the intuition. So, let's get a little bit formal and then try to define what exactly we want, right. So, this is the intuition, somehow closer points should get into the same bucket, right. So, but let us try to dig a little bit more deeper into this intuition and see how exactly can we define this process, right. So, here is a formal definition, right. So, definition. So, we are going to call a family of hash functions H, right. So, we are going to call this hash function, this family, as RC P1 P2 sensitive, and I will talk about what this means. So, basically you give me a set of functions, hash functions, I am going to call that set by a name RC P1 P2 sensitive. That's a strange name to give a set of functions, but I will tell you what that means. So, for some R greater than 0, C greater than 1, and 0 less than P2 less than P1 less than 1, and again I will explain the justification for these inequalities. If so we have like a bag of functions, and then I am going to call that RC P1 P2 sensitive if something happens, right. So, what happens if for a randomly, so if I put my, I close my eyes, put my hand inside the bag and then pick one function. So, if a randomly chosen function, let us call that function small h in h, if for a randomly chosen function h in h, the following holds. What should hold? Well, so for any 2 points x comma y in, let us say the hash functions map from R D, right. So, that is to the buckets. So, let us this can be generalized to any metric space, but then for now let us think of this as x and y are in R D. That's where we will use in most practical applications. Then x minus y less than or equal to r implies probability of x and y is greater than or equal to P1, and x minus y greater than or equal to CR implies probability that h of x equals h of y is less than or equal to P2. Okay, so let me read that out again and then I will explain what it means. We are calling a family of hash functions script h RC P1 P2 sensitive for some r greater than 0, c greater than 1, 0 less than P2 less than P1 less than 1, if for a randomly chosen function h from the family, the following holds for any 2 points in RD, right. So, the norm, the distance between x and y, if it is less than or equal to r, and that is the, the r has to appear in the condition and it appears here, then the chance that both x and y gets hashed to the same bucket is greater than or equal to P1, and if x minus y are further apart by c times r, so that is where the c makes an appearance, then the chance that they get hashed to the same bucket is less than or equal to P2. So just to give a, just to set some, put some numbers here, right. So, think of it as, let us say r is 1, c is 2, P1 is 0.8, P2 is 0.3. So, what does this mean? That we will call a family of functions as 1, 2, 0.8, 0.3 sensitive if I take any 2 points and now I pick one function at random from this class of functions and apply it to both x and y, and then let us say, now what they map to does not matter at this point. Let us say they map it to some bucket and then there is some index for this bucket, let us say. So, h of x and h of y are the indices for x and y after you apply h, where remember h is taken at random from this bag of functions. Now, if x and y are close, then we want h of x and h of y to be in the same bucket, so that when I get a query point, hopefully I will find the nearest neighbor, right. So, the closer guys should get mapped to the same bucket, that is our intuition. And now what we are saying is that, well, it may not happen all the time, but it should happen with overwhelming probability, that is, or greater than or equal to P1. In this case, I have set P1 equal to 0.8, which means that 80% of the functions in the bag that I have has this property, such that if I close my eyes, put my hand inside the bag, pick a function, then with 0.8 chance, right. So, the closer guys, when I have to quantify closer, I am saying they should be within a ball of radius r, right. So, that is by the r, right? It is the radius, right. So, the norm of x minus y should be, if it is less than or equal to r, then they get hashed to the same bucket. Now, if they are further apart, and now I have defined closeness as being within a ball of radius r. Now I will define being further apart as being, you know, at a distance of at least c times r, right. So, you know, if r is the closeness metric, c is kind of telling me how much worse than r should I be, so that I am not close, right. So, if they are really far apart, then what I am saying is that they get mapped to different buckets, right. So, let us say in this case c was 2, which means that if I am twice, I mean if I am like, think of a smaller ball of radius, let us say 1, and then a bigger ball of radius 2, right. So, if I am away from ball of radius 2, then it means that I have to go to different buckets. So, if let us say I take one point here, what I am saying is that, you know, every point within this radius r, you know, should get mapped to the same bucket with high probability, and then everybody outside this, you know, should get mapped to a different bucket with high probability, right. So, so the idea is the further guys are getting separated in different buckets, the closer guys are within the same bucket. So, remember, this is just a definition, right. So, I have not given you such a family, right. So, I am just saying that, you know, this is something that we want, and now the question that we will ask is, do we have such a family, right. So, if so, how can we demonstrate such a family, right. So, how can we argue that, you know, such a family exists, and so on and so forth. Those are the type of questions that we are going to ask, but for now all I am saying is that this is one way to say that, you know, if there is such a family, then I am going to use that family, and then just for any x, right. So, I am going to apply the h of x, so that the main advantage, remember, that I am going to get is that hopefully only closer guys are going to get hashed to the same bucket, because that is what one of the guarantees of this hash function, I mean this family of hash function has. So, which means that, you know, I am not going to miss the nearest neighbor, right. So, I might miss it with small chance, but we are anyway in the approximate world, so that is still okay, right. So, with high probability, the nearest neighbor is going to get hashed to the same bucket, and because I am only looking at the bucket where it gets hashed, I am not looking at all the data points, but only, you know, subset of data points where I am measuring distances. So, this will be sublinear. Of course, all these is, you know, I am just talking in high level, but then they have to be made precise, but we are getting there, yeah.